So you've heard me say this before, but entropy is kind of a strange thing. We know some things about it that we've learned. Over the last 2 weeks here, we're going to spend a little bit of time trying to think more deeply about, one, how we do math with entropy, but then also next week, a little bit more what entropy is. So start with some things that we know about entropy. So where does entropy come from? Well, it comes from the second law of thermo, where we have this principle where entropy is always increasing. So entropy always increases. It is allowed to decrease, but only so long as it increases somewhere else. So we use these things to be able to evaluate processes, tell us if they're impossible, if they're possible. We also use them, as we see here, to look at reversible processes. Those are things where that process causes no increase in entropy or no net increase in entropy. We also saw that entropy is a state function. It's not path dependent. So we could do calculations on this for some arbitrary path and then no entropy for no delta S for, say, a reversible path, and then that would tell us about entropy for an irreversible path. We also have ways based on that where we can calculate entropy for materials. So here we have for ideal gases, this equation down here for solids and liquids. So we know some things about entropy. It's this quantity that always increases. It's related to, as we can see in our equations, temperature and pressure. That's about it. It's kind of a hard one to wrap our minds around. We're going to write a couple things that we know and try to piece them together and then see how we could do some more calculations with that before we jump on to examples. So what is entropy? How can we describe it along a reversible path? So along a reversible path, we can describe entropy using equations something like this. ds equals dq reversible over t. We could also write delta s equals the integral of dq reversible over t, or q equals the integral of TdS. So those are all essentially the same equation. Along an irreversible path, we can't write inequalities like this. So we can write an inequality like the two that I have up there for reversible paths, but we can't for an irreversible path. So for an irreversible path, we have to write an equation something like this. We could write delta S is greater than or equal to the integral. Well, actually, for an irreversible, it's just greater than dq over t. Or we could write ds is greater than dq over t if our path is irreversible. So we flip from writing equalities, which we can along a reversible path, to writing inequalities. And that's kind of the strange thing about entropy. It's a little bit harder to pin down than, say, energy is with conservation of energy. But we can begin to write an equation, right? We have these two inequalities, but we can write it as an equality. We just have to say, well, entropy can't go down, but it can go up. So how much did it go up? Well, just let's pick a number. So let's write an equation like this. Let's write delta S is equal to the integral of our path-dependent heat transfer Q over T from say state 1 to state 2, plus some amount of entropy that was generated. We'll call it S12 gen. So this is Sgen is the entropy generated along our path from point 1 to point 2. So Sgen is exactly equal to 0 for a reversible path, and Sgen is greater than 0 for an irreversible. So this equation here now works for both reversible and irreversible paths. And it works as an equality, which is nice because then we can actually begin to calculate things. Just to think a little bit about how this ties in with work, we can take that equation that we just had and differentiate it along. So take this equation that we just wrote. Let's take the differential. So instead of delta S, it's ds. The differential and the integral will cancel out. And then instead of S gen, we'll have ds gen. So that would be ds is equal to our path-dependent heat transfer over T plus ds gen. Or we could rewrite this as dq of our irreversible path. So this is q of irreversible So if we flip this around, that's going to be temperature ds minus temperature ds gen. Just rewriting that equation up top. We can combine this with an energy balance. So energy balance delta U equals Q minus W. So we could write that we'll write these all in differential form. du equals Q along our irreversible path minus W along our irreversible path, right? Energy balances don't care if it's reversible or irreversible. Energy balances are energy balances. We could also write one of our equations, one of the Gibbs equations. We could write this as, TDS equals du minus P dV. Sorry, plus PdV. So TDS equals du plus PdV. Remember, that's just kind of an energy balance in disguise. An energy balance along a reversible path in disguise. We can combine these three equations, so this top one up here with our energy balance and our Gibbs equation, to learn a little bit more about work. So we can solve for irreversible work. And this would give us that our irreversible work is equal to P dV. That's what our reversible work is, minus a little bit. So minus TDS gen. So the irreversible work is equal to what it would be if it were reversible, minus this little bit, which is caused by entropy generation. So we call this sometimes lost work. due to the generation of entropy. So when we're generating entropy, we're having work kind of lost. So we're losing the ability to do as much work as we could. So kind of an interesting result, maybe puts, so why we would want to not generate very much entropy, or how we can make systems more efficient by decreasing the amount of entropy that we're generating. We're decreasing the amount of lost work in that system. Okay, so switching gears a little bit, we can think about performing an entropy balance using this equation. So this isn't exactly like an energy balance, but we're going to use kind of the same things. So if we do an entropy balance on a control mass, right, which is just some amount of stuff. If we look at what must be happening to entropy, the change in entropy inside of that control mass, or the change in entropy of that mass itself, is equal to how much entropy is going in minus how much entropy is leaving, plus any entropy that happens to be generated. So the way that we could write this in variables, the delta S, I'm going to write delta SCM. The change in entropy of our control mass is equal to Q in over T in. So that's the entropy going in, Q over T, minus the entropy going out, again, Q out over T out, plus the entropy that's generated, plus Sgen. So this is a useful equation to be able to look at how systems generate entropy, or how larger scale processes actually generate entropy. We'll do a couple example problems using this equation in 2 other videos, so make sure to watch those. This is a deceptively easy equation. It's actually pretty challenging to figure out what to put where. So watch the example videos and hopefully get a sense of how to use this equation so we can actually calculate entropy.